All right, let's try this a few more times. In a psychology lab, researchers are studying the color preferences of young children. 6 green toys and 4 red toys, identical apart from the color, are placed in a container. The child is asked to select 2 toys at random. What is the probability that the child chooses 2 red toys? We have options, right? So this is the idea that you're going to pick one toy and then you're going to pick a second toy. So it's like 2 separate events where we're dealing with probabilities. When we're dealing with a sequential amount of events, that would be a good time to use a tree diagram. So sequential, as in like a sequence of things, a sequential event is good for a tree diagram. So what we're going to do is we're first going to start off with the first event. We can either pick a red toy or a green toy. We have a total of 10 toys, right? 6 green and 4 red. So we have a total of 10. The probability of picking a red one is 4 out of those 10. So that would be a probability of 4 over 10. You don't have to simplify it. It's totally fine just leaving it as 4 out of 10. The probability of picking a green toy would be 6 out of 10, right? So we're just breaking out this idea of picking a toy out one at a time. It doesn't tell you one at a time. You could pick 2 toys out at the same time, but it's still this idea of picking one out, not replacing it, and then picking another one out, right? That's the same thing as just picking 2 toys out at the same time. We've picked out a red one. And if we've picked out a red one, we can then go in and pick out a second one for red and green. Now our probability shifted just a little bit because now if we've picked a red one, we have 1 less of our total, right? So we're dividing now no longer by 9 or by 10, we're now dividing by 9. So we're no longer dividing by 10 because we took a toy out already. Now we're dividing by 9 for both of these guys. And then you have to figure out, well, how many reds are there left? If we picked a red, that means one of those 4 are now gone, which means we only have 3 reds left. So the probability of picking a red and then a red is 3 out of 9 and 4 out of 10. Okay, so that's the path on this, which is what we're going to use, but I want to finish making the tree diagram. So hold on one sec. If we picked a red first and then we picked a green, we still haven't picked any green before. So you still have your total of 6 green toys, just now out of 9 in the bag instead of 10. Now we do it again for the green path. Let's say that we picked out a green toy. Well, we now have 1 less toy of the total, so we're now dividing by 9 instead of by 10. And now if we want to go to red versus green, if we picked green first, picking a red then means that we haven't picked a red first. So all 4 of our original 4 red toys are still in there. So the probability of picking a red on this track is that we have 4 toys that are still in there, just now out of a total of 9. Versus picking a green and a green, we've picked a green already, which means that there's 1 less green in the bag, which means now we have a total of 1 less of 6, which is 5. Okay, so that's the idea of the tree diagram, is you just kind of follow through paths. First we go here, and if we go here, then what does that mean for the next step? And it could be that you've taken a toy out and left it out, or maybe it could have been that you left the toy in. If you left the toy in, then it would be 4 tenths, 4 tenths, right? It would be 6 tenths, 6 tenths here. Your probabilities wouldn't change if you put everything back in. If they're totally independent events, then your probabilities don't change as you move forward in the tree diagram. But if they are dependent events, if they rely upon each other, then your probabilities change as you build the tree diagram. Okay, so when we're talking about the probability of picking 2 red toys, 2 things have to happen. We have to first pick a red, and then we have to pick another red. What operation do you think we're going to be using here if we're going to pick a red and then another red? The key here is the word and, right? It's not pick a red or pick a green. If it was pick a red or pick a green, it would be 100%. Those are the only 2 options, right? No matter what we pull out, it'll be either red or green. The probability is high. But if we picked a red and then another red, think about it, the probability is getting smaller because we're getting a little bit more picky about what we're looking for. Okay, so picking a red and then picking another red is a very small probability. And how we get small probabilities is we multiply. The word and means multiplication. Try it out when you're like trying to figure out what operation you want to use. Say like, okay, would it make sense that this would be a red or a red? That doesn't really make sense because or implies another option. A red and a red then implies that we've got two specific occurrences that have to happen at the same time. Okay, so now that we know that it's multiplication, now we need to take our probabilities of each of those events happening. First, picking a red, the probability is 4 out of 10. The second picking of the red is 3 out of 9. So we take those two probabilities and we multiply them together. You can use your calculator for sure, or you can just remember how to multiply fractions. Remember how we multiply them is we multiply them across. 4 times 3, 12. 10 times 9, 90. You can leave it like that, or you can leave it as a decimal, which is 0.133. All right, second page. Example 6. An experiment to study the phenomenon of color blindness. In an experiment to do this, researchers collected information concerning 1,000 people in a small town and categorized them according to color blindness and gender. The table shows the summary of the findings. It's kind of like a thing with color blindness that females don't really get colorblind as much as males do. So then that's kind of why they're talking about color blindness versus gender. So what is the probability that the person chosen at random is colorblind given that the person is female? So this word given here means that we need to do that dash or that line down. So what's the probability that they are colorblind given that the person is female? And you can either remember the formula that it's the probability that they're colorblind and that they're female divided by the probability that they're female. You can try and think about it logically and saying, okay, if I'm given that they're female, that means I'm only focusing on the females, which means my total has now changed. My total has now changed to just females. So you've now shifted your focus to just females. And you're saying, what's the probability that they're colorblind? So then you take the colorblind people in that female category and divide it by the total females. That's all this is saying. If you're a formula person, use this formula. And I do believe that it's in your formula packet. If you're not, you can always logically think through it. All probability is very much a logic game, which can be really frustrating when you don't understand the logic, like a riddle, right? I find riddles very frustrating, but also very satisfying when I figure it out. That's the same thing with probability. It's a riddle, and you have to figure out what do these words mean and what do they imply and what's the situation that we're looking at. Okay. So probability of colorblind and female, that is just 2. We only have 2 colorblind females. The probability of just female, so that's all of your females totaled up, and that's 490. Writing that as a decimal, we get 0.04, which means 4% of all of your females were colorblind. Very small. What is the probability that you picking a person at random that they are a colorblind female? So the probability of a colorblind female is you find the colorblind female. So colorblind female divided by just the total. We're not given something. It's not colorblind and female, which, yeah, no, it's not colorblind and female. It's a colorblind female. Right, a colorblind and female would be what's the probability that we picked a colorblind person, and then what's the probability that the second person we pulled was a female person. And so those are 2 separate events. This is one event, and they have to both be colorblind and female. So it's 2 still, but now we're not just looking at females, right? We're looking at everybody. So this is out of your grand total, which is 1,000. Dividing that out, 0.002. Less than 1% of those people that you looked at were colorblind female. What about a color-blinded individual? See if you can do this one on your own. Okay, so a color-blinded individual, you need to find the colorblind person and just divide it by the total. Very straightforward. All of your colorblind individuals added up to a total of 42, divided by your grand total, which is 1,000, you should have gotten 0.042. Last example. One national airline is known for its punctuality. The probability that a regularly scheduled flight departs on time is this, and it gives us the probability. The probability that it arrives on time is this, and the probability that it arrives and departs on time, which is represented here by the intersection, right? It arrives and departs on time is 0.78. Find the probability that a flight arrives on time given that it departed on time, okay? So the probability that it arrives on time given that it departs on time. Given that it departs on time means that your total is now the probability that it has departed on time. You're only looking at the flights that have departed on time. That's the only thing you're looking at. Then you need to look at what's the probability that it arrived and departed on time. You're given those probabilities. That's 0.78 divided by 0.83. Go ahead and divide that out for me. You should have gotten 0.94. Go ahead and do this last one on your own. We want to know the probability that it departs on time given that it arrived on time. And from our previous example on the last page, we realized that these are going to be different numbers because we're changing what we're focusing on. Now we're only looking at flights that have arrived on time, and then how many of those also departed on time. So we're only looking at the flights that arrived on time. We're saying, okay, well, how many of those actually departed on time? So the intersection of those guys are always going to be the same. It doesn't matter. But now we're going to be divided by the probability that it arrived on time. Dividing that out, you should have gotten the decimal of 0.85. All right, good job today. These are all of your operations. So by now, you should start feeling confident and comfortable with knowing when to add and knowing when to multiply your probabilities. So you add when you use the word or, you multiply when you use the word and. And now we have a new word that we're adding into our operations of probability. The new word that we have is given. We have that something is given, or this idea of we're now only focusing on this certain group of people. We're changing the total that we're looking at. We have this formula. I like formulas. I enjoy them. They feel like a recipe to me, and I just plug it all in, and then I just go and it works. If you're not a formula person, just realize that you're just changing what you're focusing on, that you're changing your totals, and that's it.